Hello, statistics class. Welcome to another week of distance learning in statistics. And this week we will be learning section 9.2, modeling the distribution of sample proportions. So, before we do this, it's important to have an understanding of what a sampling distribution is, which is what we talked about in section 9.1. As a reminder, or as a review, the sampling distribution of a statistic lists all possible values of a statistic and how frequently they will occur. For each possible statistic, such as range, median, proportion, etc., each possible statistic has its own sampling distribution. So, we did the example with picking, I think it was red and green chips, right? And in our simulation, that wasn't a sampling distribution because it wasn't all possible samples. So it was just 25 or 50 of them. But what we can do is estimate the sampling distribution using an experiment or simulation like we did. And that is the goal of statistics. It's about making inferences about a population from a sample, right? Because you can't always figure out information about the entire population. It might just be way too large, right? Like the population of the United States. You might have to take a sample to represent those people. So this is all about making accurate representations using a sample to predict or estimate or make approximations about the population. So, once again, your assignment will be to take notes, and you will have one problem set from Khan Academy this week, not from the book. All right, last 2 weeks we did it from the book. We're going back to Khan Academy. So one of the major tasks of a statistician is to discover the proportion of individuals in a population who possess a certain property or characteristic, and you've certainly been seeing this issue in the news, right? Because we're not in school because of coronavirus. You know that there's an issue where we don't have all the tests, so we're not testing the entire population of the United States. We're only testing those who probably have symptoms. And even narrowing it down more, not just those who have symptoms, but those who are at risk. So is the sample that we have right now a good sample to represent the entire population? Probably not. But if you think back to our chapter on sampling and what is good sampling and bad sampling, that's really what the issue is. And sometimes it's just not practical to take good samples because there's a financial barrier even to sampling, right? We can't just give random samples to 50 individuals in each state, or random samples just by randomizing everybody in the United States and picking a random person and testing them for COVID. That is not practical because we do not have the test. So, yes, the sample is not a perfect sample. So, anyways, that was just a side note. So another example could be the proportion of U.S. residents who are unemployed, which is another issue right now, or the proportion of Herman High School students with at least one AP class, right? This is looking at a population. So, and without a census, we'll never know the true value of P, the population proportion. Instead, statisticians will estimate P by taking a sample and computing the sample proportion. So we take a sample of the population. If we're going to be focusing on proportions, next section will be on mean. So it's just a different number summary. So we're completely focused on proportions, which is basically percent of a population, or you can put it as a decimal. That's what we mean when we say proportions. Okay. So in section 9.1, we learned that p-hat is an unbiased estimator P. If you need to go back to see what unbiased estimator really means, you should go back, but I gave a quick little summary here. This means that the mean of the sampling distribution of p-hat is always equal to the parameter p. Recall the chip activity and example we did. So when we take a sampling distribution of a sample proportion, and it's all possible samples, there's going to be some sort of distribution, probably a normal distribution. The mean of all those values is going to be directly in the middle, right? It's going to be the middle of the normal distribution, all right? And this is really what we mean by unbiased estimating. So the mean of the sampling distribution of p hat is exactly p. We talked about this last time. We didn't go really into standard deviation, so this is new. The standard deviation of the sampling distribution of p hat is the square root of p times 1 minus p divided by n. So as a reminder, what does p represent? P represents population proportion. N represents sample size. So we need the sample size and the entire population proportion, which isn't always going to be possible to figure out. So the whole goal here is we're going to be making inferences about a population from a sample. That is like the goal of statistics. Take an educated guess or an estimate about the entire population when you're only given a small piece of data, a sample. The first issue being that the sample needs to be a good sample, and that's kind of the problem we're having right now in the United States. So, or even around the world. So, there's two rules of thumbs here. To make these inferences, there's two rules of thumb. The first, use the formula for the standard deviation we talked about up here, a p hat, only when the population is at least 10 times as large as the sample. If the population was, for example, only twice as large, then we have a very big chunk in our sample. So let's say there's 400 million people in the United States. If we have a sample of 200 million people, right, the population is only twice as large as the sample. That is a pretty good sample, and we don't really have to get too much crazier into making any sort of analysis, because if we have half of the entire population, that's going to be enough data right there to not have to go through this whole process. So you take 200 million people from the United States right now, test all of them for COVID-19, and 3% of them, I'm just throwing that number out, 3% of them have it, you can be pretty confident that 3% of the population has it, because it's such a big sample. All right? And the standard deviation will be very small for p hat in that case. So this is kind of, if there's a formula, it's this right here. Capital N is greater than or equal to 10 times lowercase n. So we're going to only use this formula for standard deviation when this is true. Capital N is population size. Lowercase n is sample size. All right, so this formula is basically this in words right here. The second rule of thumb, we can use a normal approximation for a sampling distribution of p hat, which is very handy for finding certain probabilities. So use the normal approximation for the sampling distribution of p hat for values of n and p that satisfy n times p is greater than or equal to 10, n times 1 minus p is greater than or equal to 10. All right, so you know what n means, sample size. You know what p means, population proportion. What this is really checking is just to make sure that our sample size is big enough relative to the actual population proportion. So for example, if the sample size was only 2 people, we wouldn't be able to ever use the normal approximation. It's not big enough, okay? If p was ever equal to 0, 0 times anything is not greater than 10, 0% would mean that the sampling distribution, well, it would be extremely skewed to the right. All right, so it's definitely not normal. So this is when p is equal to 0. So this will not work. All right, so we just need to check these two things. That's one thing. If we're going to use a normal distribution, if there's one thing to take away from this, check these two conditions. Otherwise, can't use a normal distribution. All right, so I've been rabbling. I guess rabbling is the word. Where's my other paper? Crap. Example 1, where are you? I think the dog ate it. 1 second, I have to pause. Megan, is there a piece of paper downstairs with some math stuff on it? No. Okay. So, using what we've learned about the sampling distribution of p-hat, we can determine the likelihood of obtaining a simple random sample in which p-hat is close to p. Okay. So basically these problems that we're going to be doing, the only really problems you're going to be doing this week, are going to be finding the probability or the likelihood of obtaining a certain random sample, a simple random sample, in which the sample proportion is close to the population proportion, which is the goal, right? So we're going to be finding probabilities that I take a sample and it is close to the actual proportion for the whole population. All right. So, first example. A polling organization asked an SRS of 1,500 first-year college students whether they applied for admission to any other college. So, basically, whether they applied to any other college, right? In fact, 35% of all first-year students applied to colleges besides the one they're attending. So, basically, applied to more than one. That's 35%. What is the probability that the random sample of 1,500 students will give a result within 2 percentage points of this true value? So, we're finding the probability that this sample, of this certain sample size, will give a result within 2 percentage points of this true value. So basically this is saying, what's the probability of getting a sample that's between 33% and 37%, knowing that the population proportion is 35%, right? So we know that ahead of time. So we're really just looking at probability of getting a certain sample, knowing the population proportion. So, first thing to note, this is a simple random sample. Sample size is 1,500. The population proportion, which is a parameter, is 0.35. Remember, that's what P represents. So, first, let's talk about the mean of the sampling distribution of p-hat. That is equal to P, always, right? So it's 0.35. That's what we talked about for an unbiased estimator. And it's also right here. So the standard deviation of the sampling distribution for p-hat. Before we calculate it, we need to use rule of thumb number 1, which is on the previous piece of paper. Is capital N greater than or equal to 10 times lowercase n? Is it? Well, capital N we don't necessarily know, but we know lowercase n is 1,500, right? There's 1,500 first-year college students. 10 times 1,500 is 15,000. Now, just using your common sense, capital N, as a reminder, I wrote it on the last page, is population size. Our population here is first-year college students. Are there more than 15,000 first-year college students? Are we saying in the USA, in the world? It doesn't specify. But either way, whether it was USA or the world, there are certainly more than 15,000 undergraduate first-year college students, right? You can think like UMaine alone, I don't know, has probably like 3,000 or 4,000 freshmen, right? So it's definitely true that when we're looking at the entire population of first-year college students, it's more than 15,000. So rule of thumb number 1 is a yes. So that means we can use the standard deviation formula. So the standard deviation formula is P, 0.35, times 1 minus P, divided by lowercase n, which is 1,500. 1 minus 0.35 is 0.65. Now I just went to the answer from here, and I'm going to tell you it's just because I would do everything now in the calculator, so you can prevent any round off error. So I'm going to turn my calculator on. I'm going to clear everything. I'm going to do 0.35 times 0.65. I'm going to get that answer. Then before I write it down, I'm just going to divide 1500. So that's right here, right? And multiplied, then divided. And then take the square root of that answer. So I'm going to click my square root button, which is second x squared. And to get this entire answer right here, instead of writing it, I'm going to click second answer down here. And it's going to copy and paste that. And that's the answer. So now I can round, and in general, we're going to round the standard deviation to 4 decimal places. So that would be 0.0123. So that is the standard deviation of the sampling distribution of p hat. Okay? We checked it using the first rule of thumb. Now we're going to check the second rule of thumb. Can we use a normal distribution to approximate the sampling distribution of p hat? That's the only way we're going to calculate these. So if this is a no, the problem's done. All right? So these are the two formulas. First, let's just look at this part. N times P needs to be greater than or equal to 10. Lowercase n, sample size is 1500, P is 0.35. Remember, this is all the stuff I was given and you should have written down already. 1500 times 0.35 is 525, way bigger than 10, so that checks out. But we also need to check the second part of rule of thumb number 2, which is n times 1 minus p is greater than or equal to 10. N is 1500, p is 0.35, so we subtract inside the parentheses to get 0.65. 0.65 times 1500 is 975, which is way greater, way larger than 10, so that's a yes as well. So yes, the normal approximation will be quite accurate. So we're going to use that normal distribution to actually answer the question right now, which going back, you might have lost track of the question because we went into these rule of thumbs to try to answer it. The question is, what is the probability that the random sample of 1,500 students will give a result within 2 percentage points of this true value? So I actually ran out of space, so we're going to the back. All right. The true value, I'm just going to rewrite it here, was 0.35. The question saying, what's the probability that we're going to fall, the sample we choose is within 2 percentage points. So I subtracted 2% and added 2% to get 0.33 and 0.37. That's really what it's asking. Find the probability that the sample proportion p hat falls between 0.33 and 0.37. So I'm going to set up my normal distribution since we said we can do that with rule of thumb number 2. The mean of the sampling distribution of p hat is 0.35. And I want to find the probability that p hat falls between these two values. So I'm going to shade this area. We're using a normal distribution. So we're going to basically be doing the same normal distribution process that we've been doing forever. So the mean always goes in the middle. We're going to use the z-score formula, which is p hat minus the mean of the sampling distribution of p hat divided by the standard deviation for the sampling distribution of p hat. This we found already on the previous page is 0.0123. This is always the mean, 0.35. And 0.37 is whatever really the p hat of interest is. So we're going to do that with 0.37. We're going to do the same exact thing with 0.33. Right? So we have two formulas going at once here. The only difference is I plugged in 0.37 for this here, and I plugged in 0.33 for p hat here. And then we're going to calculate 0.37 minus 0.35. 0.02, right? It's within 2 percentage points. So divided by 0.0123. And I'm going to round the 2 decimal places for a z-score. So that 2 is going to become a 3. Oh, I have the negative signs backwards here. So this is positive 1.63. And this one should be negative 1.63. That's negative because it's just 0.33. Oops. whatever. 0.33 minus 0.35. Divided by 0.0123. Negative 1.63. Okay. So those are my z-scores. That was the first step. Now I'm going to use the table in my book to find shaded area. If you don't have your book, all you need to do is Google, you could say z-table. Alright? They're all pretty much the same, but you want to make sure that the z-table you're using is the same basically that we have in the book, where the table entry for z is the area under the standard normal curve to the left of z. Sometimes you'll see like in between two values like 0 and z. You don't want that. You want it to the left. Okay, so we have our two z-scores. 1.63, negative 1.63. So I'm going to start on the negative side since that's the first page. Negative 1.6 lines up with 3 right here. That's 0.0516. Okay. So 0.0, I just drew the picture again. So to the left, negative 1.63 is 0.0516. And then I'm going to look up 1.63 on the second, on the back. Oops. Alright, this is going to be hard to maneuver here because I don't want to move my dock camera around. It's just annoying. So 1.63 is 0.9484. 0.9484. And so you'll see that right here. Okay. So that was using table A in the book. So if I want to get between these two values, I know that this whole part to the left of this is 0.9484, and the whole part to the left of this is 0.0516. We just subtract, and we'll get the shaded area. So I have some fancy symbols here. You'll see the actual subtraction going on here, like I just said. But all this means is, so capital P like this will mean probability. The probability that P hat is between 0.33 and 0.37 is the same as the probability that Z is between negative 1.63 and negative 1.63. And that's just these two numbers subtracted, which is 0.8968. That is our answer. That's what we did all this work for. So what is that really saying? Let's answer the question. That should really be, oh, that's what step 3 is, right? Answer the question. Well, the question was, what is the probability that the simple random sample of 1,500 students will give a result within 2 percentage points of this true value? That is the probability, about 90%. So almost 90% of all samples will give a result within 2 percentage points of the truth about the population. So that means in this situation, with a sample size of 1,500, we can be pretty confident that our sample that we choose is pretty accurate in terms of the proportion, right? It's within 2 percentage points of the actual proportion 90% of the time. All right. So that's kind of just like finding the probability that your sample is going to be good. A good sample is very powerful because we need good samples to make inferences about the population. And you've probably started to notice that in the news, right? If we don't have a good sample, we can't make a prediction about what's actually going on with the entire population. So, all right, well, I'm just going to do another example. To be quite honest, if you were comfortable solving that, I don't mind if you really stop taking your notes right here. But you're going to have a bunch of these problems on Khan Academy, so I would suggest you stay and we'll do another example together. So, suppose that 43% of registered voters in Arizona are Democrats. What is the probability that there will be less than 30% Democrats in a random sample of size 50? Oh, my battery's running low. Let me just plug this in real quick. Alright, so n equals 50, right? Lowercase n because it's sample, not uppercase. P, which is population proportion, is 43%, so 0.43. The population here, it's always good to know what the population is, otherwise P and P hat might not make sense. The population is registered voters in Arizona. So the percent that are Democrats is what P represents, 0.43. And it says, what is the probability that there will be less than 30% Democrats in a random sample of size 50? So what's the probability that our sampling proportion will be less than 30% or 0.30, same thing. That's really what we're finding. So we need to use a normal distribution to solve this. So we're going to first see, can we use a normal distribution and the standard deviation formula. So again, the mean of the sampling distribution for proportions is the same as P, which is 0.43. So it's kind of a given. The standard deviation, we're going to check rule of thumb number 1. Is capital N greater than or equal to 10 times lowercase n? So lowercase n is 50. 50 times 10 is 500. Are there more than 500 registered voters in Arizona? What do you think? Using your common sense, yes, Arizona probably has a couple million people, at least, right? There's definitely more than 500 registered voters in the population. So that's a yes, so we can use the standard deviation formula. Alright. My dog's supposed to be hypoallergenic. We got her yesterday. I'll bring her up later. You have to watch till the end though, because there's no way you're going to skip. Alright, so the formula is P times 1 minus P. 1 minus 0.43 is 0.57. So that's how I got that. Divided by lowercase n, which is 50. So again, in our calculator, we're going to do 0.43 times 0.57. Get our answer. Divide by 50. Take the square root of the answer. And then we only round to 4 decimal places, so that's right here. The 1 means don't round this up, so it's 0.0700. I could have just written 0.07, but I wanted you to know that I rounded out 2 decimal places, so I wrote, or rounded out 4 decimal places. Okay, so we have our standard deviation for the sampling distribution for proportions. Now, can we even use a normal distribution? That's where we use rule of thumb number 2. So first we check n times p is it greater than or equal to 10, and then second we check n times 1 minus p is it greater than or equal to 10. So let's start with the first. N is 50, p is 0.43. What's 50 times 0.43? It's 21.5, which is indeed greater than 10. So that's a yes. N times 1 minus p is it greater than or equal to 10? P is 0.43. 1 minus 0.43 is 0.57. 50 times 0.57 is 28.5. Yes, that is indeed greater than 10. So we can use the normal distribution. How exciting. So I made this picture. I would suggest making pictures. The mean, always in the middle. P hat. Well, let's question what we're at. What this is asking. P hat less than 0.3. What's the probability that P hat is less than 0.3? So we're going to shade to the left, less than. We're going to use the z-score formula. P hat is 0.3. The mean is 0.43. We subtract those and divide by the standard deviation we found here. So we do that out. 0.3 minus 0.43 divided by 0.07. We're going to go 2 decimal places, so negative 1.86. Step 2, use table A to find the probability that Z is less than negative 1.86, because the Z here is negative 1.86. We want to the left of it. So we're going to use table A in our textbook, and we're going to go to negative 1.86. And of course, like I said before, this is online. Just Google Z table. Negative 1.86. 0.0314. Okay. So that really is the final answer. There's a 0.0314 probability that there will be less than 30% Democrats in a simple random sample of size 50. So, if you know exactly how many registered Democrats there are in any state, and you want to sample 50 people, there's a probability that in that sample, there's a 3.14% chance that there'll be less than 30% Democrats in that sample, as long as there's 43% in the population, right? So it's pretty unlikely to get from a sample size of 50 less than 30% Democrats just in that sample. So that's just, again, finding the probability that a sample is accurately representing a proportion. And of course, as n gets larger, as our sample size gets larger, it's going to be more and more reflective of the population. A bigger sample size is always better. Always. Okay, so switching up the question a little bit. Same question, but now it's, or same given information, but the question is now different. N still equals 50. What is the probability that the sample proportion will be within 0.05 of the true proportion? So we already checked our rule of thumb 1 and 2 up here, so we're going to go right to the normal distribution calculation, and I'm going to draw a picture. So it says, what is the probability that the sample proportion will be within 0.05 of the true proportion? This is the true proportion. So within 0.05 means greater than 0.38 and less than 0.48. So we just take 0.43 plus 0.05 and 0.43 minus 0.05, and that's how I got those two numbers. Right? So we're finding that the probability falls within those two numbers. So again, we're going to use our Z formula. So I'm going to start off for 0.38. So we have p hat minus the mean divided by the standard deviation. The mean and the standard deviation that we found before, p hat that we have from the question. 0.38 minus 0.43 is negative 0.05. Divide that by 0.07 to get negative 0.71. So we do the same thing for 0.48. We subtract, divide, and we get 0.71. So we have the negative 0.71 and 0.71. We're going to look in table A for negative 0.71. That's actually right here, 0.2389. And then we're going to look at positive 0.71. It's right here, 0.7611. Did I do that right? 0.7611. I did this wrong. 0.7611 and 0.2389. So 23.2389 is to the left of this. 0.7611 is to the left of this. So we subtract those, and we get 0.2389. I used the table wrong before. Okay, so that would be 0.7611 minus 0.2389, 0.5222. Okay. So, answer the question. There's a 52.22% chance that the sample proportion will be within 5% of the true proportion. So if I take a sample of 50 people in the state of Arizona, there's a 52.2% chance that my sample will have between 38% and 48% Democrats. Again, how accurate is our sample? That is what all these questions will be asking. So there's kind of 3 examples of what you're going to be doing on Khan Academy. As you can see, each question might take a little while, but I only gave you 1 problem set, and I think it's 4 questions. Now I'll show you my dog. This is Meadow. And this is Megan. Say hi. She's very cute. She's cuter than your dog. Bye.